A lighthouse is located on a small island 4 kilometers away from the nearest point P on a straight shoreline, and its light makes 5 revolutions per minute. How fast is the beam of the light moving along the shoreline when it is 1 kilometer from P? So here's a situation. We have a shoreline and an island. Let's say this is a straight shoreline and the island is, say, here, and on the island they have a lighthouse. So here's a lighthouse. And let's say this is a lighthouse. So they give us that this one is 4 kilometers away from the nearest point. Say this is the point here, and we have this length is 4 kilometers. And they also give us the rate here. The light makes 5 revolutions per minute. 1 revolution means that this one rotates 2 pi radian or 360 degrees. Let me draw that. The light beam, for example, look like this, and it keeps rotating. Keep rotating. 5 revolutions per minute. So let's draw that at one moment here. At this point, it receives the light from the lighthouse. So we have an angle like that, theta, and this light beam keeps moving. And 1 minute is moved 5 times full circle here. So we have d theta over dt is 5 times revolution, so 5 times 2 pi. It's like 10 pi radians per minute. Yeah. So that is the first sentence. Now, how fast is the beam of the light moving along the shoreline when it is 1 kilometer from P? So let's say I have at one moment is 1 kilometer from this point P. So we have the distance here. This length, let's call it x. So at the time, at x equal to 1 kilometer, how fast is the beam of the light moving? So at the time, this is 1, x equal to 1. What is dx over dt? How fast is the beam of the light moving along the shoreline? So let's compute that. We need to set up the relation between 2 functions here, theta and x. Theta and x both depend on time. In this case, we have this right triangle, tangent theta x over 4. That is our relation. And all we need to do is to derivatives both sides. So d over dt, tangent theta, d over dt, x over 4. So remember that theta and x are functions depends on t. So we need to change rule. Tangent prime secant square theta times d theta over dt. That's the left hand side. Right hand side 1 over 4 dx over dt. Yeah, so the only difficult step here is you need to do the chain rule for this tangent. Secant, tangent, remember that. Tangent prime secant square, that's why I have this, and I use the chain rule. So now you have secant square theta d theta over dt is equal to 1/4 of this. The time we are looking at is the time when x equal to 1. X equal to 1. We know that d theta over dt is 10 pi. d theta over dt is 10 pi. This one always d theta over dt only 10 pi. That's one we know. X we know. Because x and theta are related by this formula, you can compute the angle theta then. This relation will help us to compute the angle theta at that moment. So we know that at this moment, tangent of theta is x over 4, which is 1/4. Tangent theta is 1/4. So one formula you should know. Tangent, the relation between tangent and secant. So if you don't remember that, secant square is 1/secant is 1/cosine. Cosine square. 1/cosine. 1 is sine square plus cosine square over cosine square theta. The first term is tangent square theta. The second term cosine square over cosine square plus 1. So now you can use that. Tangent theta is 1/4. Tangent square 1/16 plus 1. So this is 17/16. That is secant square. Secant square. So now everything is known except what we need to compute, dx over dt. Let's plug that in. Secant square is 17/16. d theta over dt is 10 pi. 2 times 5 pi. So cancel that 2 out anyway. 1/4 dx over dt. The 2 we can cancel that out. So you have 17/8 times 5 pi 1/4 dx over dt. So you can cancel that's 4 out too. Dx over dt 17/8 5 pi times 4. 17 times 5 pi divided by 2, which is 85 pi divided by 2. This is dx over dt at that moment. And that is our final answers. That is how fast the beam of the light is moving along the shoreline.